So welcome back to this afternoon session. So we continue with Paula Giraldo, who is a professor at the physics department in Universidad in Bogotá, Colombia. She did her PhD in physics in Stanford, was a postdoc in the National High Magnetic Field Laboratory in Tallahassee, Florida, and she continues her collaboration with them, if I understood well. And now she will tell us about revealing the electronic structure and topological states of charge density wave compounds. Paula, gracias.
Thank you, Bernardo and Rafael, for inviting me here. So I'm the outsider. I'm the only experimentalist here, so behave.
You're also.
You are also an experimental. Oh, thank you. You helped me to answer the questions. So I want to give you a perspective on, you talk about these topological materials and all these nice properties, but I'm here to be the carrier of bad news. Not everything is ideal. Not everything is easy to measure. It implies a lot of work and a lot of technical skills in order to actually reveal all the nice predictions that you are doing with your calculations. So the example I bring today is the closest one to this story and this message that I want to give you, because it's a system that it's predicted to have topological properties. It's supposed to be some Dirac points in its band structure. And it is also a charge density wave material, which kind of it's a little bit outside of the things that you have been mentioning here. So it does have interactions. It does have many body interactions. And in addition to that, it has disorders, or it mixes other things that you have talked about. And it is very hard to actually determine if something has topological properties when you don't really understand all the different other electronic states that come around with real materials. So the idea is to give you a little flavor of how you actually try to determine if something is topological by first understanding all the other things that not necessarily are topological. All right, so the material I'm going to talk about, it belongs to the tetrachalcogenide, transition metal tetrachalcogenide system. It has two main members, tantalum tellurium-4 and niobium tellurium-4, and these are quasi-1D materials in which you have chains of metallic ions that are surrounded by tellurium, and they interact with van der Waals forces with other chains. So we have done the work of trying to experimentally determine the electronic structure, not with ARPES measurement. We do have some ARPES measurement in our crystals, but we specialize at determining the thermodynamic or bulk electronic structure of this compound, which can also have some information about possible topological or surface states in this compound. So we do a high magnetic field magnetoresistance in these compounds at different angles, and today I'm going to show you how you can actually reconstruct the full shape and topology of the Fermi surface through this kind of measurements. And then the message, if you fall asleep along the way, don't worry, here's the conclusion. The conclusion is that this material is actually very complicated. And it has a Fermi surface that comes from a reconstructed charge density wave in order, but it also has some portions of this Fermi surface that do not reconstruct well from the Fermi surface itself. So it mixes both worlds, a non-reconstructed Fermi surface and a reconstructed Fermi surface. And besides that, this compound niobium tellurium-4 also has some intricacies, some difficulties in terms of the charge density wave order that I will discuss. And we can, through these kind of measurements, we think we have signatures of the possible topological nature of this compound. So it just gives you a nice playground in order to start actually trying to understand what could be the relation between topological states and charge density states. All right, so that's my conclusion. We know nothing. We know that it's complicated. That's it. All right, so I want to give you some flavor of where I come from. So I did all my formation, my studies here in the US, and now I went back to Colombia and I started my own group in Universidad de los Andes, which is in Bogotá. So this is the campus of the university. My lab is right here next to the mountain. So here there is a little virgin statue that is right on top of the mountain. It's really, really beautiful. And we are right close in the mountain. So you need, if you go to visit us at some point, you will have to climb a lot of steps. So you won't have much air. We are 2,000, we're 7,000 feet above sea level. So this is the highest you can get. And then this is my group. We are here right in the middle of Colombia. And our group is really good at growing crystals. So we move in the frontier with chemistry. We synthesize our own single crystals. And we have that flexibility of tuning electronic properties of these compounds through chemical doping. So for example, this is a transition metal dichalcogenide in which we have found that by doping tellurium into tungsten diselenide, we found multiferroicity in this family of materials. And this gives or open the gate to multiferroic two-dimensional devices, which are very promising. So we are very happy about that. And in addition, I'm going to talk about these kinds of crystals, the tantalum tellurium 4, which are quasi-1D crystals, and we can actually dope these compounds as well. I'm not gonna show today some results of the dope compounds, but we have the flexibility of also tuning the electronic properties of these crystals with chemical doping. And besides that, we do materials characterization. We combine multiple probes in order to find and to arrange this puzzle of all the different properties and have a global understanding of the properties of these compounds. And the ones we cannot do, we do through collaboration. So I'm very happy to collaborate with you. So we mainly work in topological materials. It's one of our lines, which I am a starter in the field. We do multiferroic 2D materials, also starter in the field. And I have most experience in superconducting systems. But these are very nice studies that I invite you to check out. So before I start, let me introduce you to my collaborators and the people that have made possible this that I'm presenting today. So my students in Uniandes, my graduate student and my two master students. So I have collaborators that have performed the ARPES measurement of the samples I'm going to show today in Universidad Paris-Saclay and Minas Gerais in Brazil. Collaborators that have helped with DFT calculations in Colombia and in Belgium, and collaborators for STM measurements in different groups in different places, and my supporter in the MATLAB for the high field measurements that I'm going to focus on today. And this is the funding agents that I've worked with. All right, so topology and correlated states. So we mainly know, and we have talked about some of the systems that show mainly superconductivity and topological states, which give rise to interesting states of matter, like Majorana modes, and this is my favorite example of Meissner effect, back then when they had room temperature superconductors in the movies. But then we have other correlated states of matter as well, not only superconductivity. So we have charge density waves. And there are several predictions in theory, although a much lower volume of works in understanding the intersection between charge density wave and topological states you can find in the literature. But nevertheless, there are some predictions of the existence of axion insulators which can rise in the intersection of these two types of physics. So this can lead to what's called axion strings, which are ways in which you can transport current with no dissipation in this kind of system. So they are very interesting also in the application side. So let me focus on this topic. So before, a very fast review of what the hell is a charge density wave in case there is any mathematician in the group that does not know what's a charge density wave. So charge density wave is a periodic arrangement of the charge density. If you have just a simple metal with a parabolic dispersion, you fill electrons up to the Fermi level, And you have a periodic in this landscape of electronic structure, you have your ions and you have a flat arrangement of electrons. They are completely delocalized in real space. But once you turn on interactions between the lattice and the electrons, you modulate, your system is unstable to the modulation of this charge density, which takes an arrangement which creates a new periodicity in your system, which is exactly the 2 times the Fermi wave vector. So this is for a half filling case, which gives you a double periodicity here, double periodicity. And this instability, or this new periodicity, of course, opens a new gap in the right at the Fermi surface. So the material tends to become an insulator. This is called Peierls instability, and it's the competition between the energetically favorable way of lowering your electronic states with a cost of elastic energy because you're putting atoms closer. So if you have, like in this case, you create a commensurate charge density wave, meaning that the new periodicity that you get is an integer number of the lattice periodicity that you had originally. But this happens only for very special fillings of your bands. If you have any type of filling or in more complicated Fermi surface, you generally get what's called an incommensurate charge density wave, which has a new periodicity that is not a multiple integer of your lattice periodicity. So in this, for this state, the message here is that for one-dimensional system, your electronic susceptibility is really unstable to the formation of a charge density wave, because you have here a divergent term each time you connect some states of the same energy with the same wave vector. So in one dimension, you have a Fermi surface that is composed of 2 points that are perfectly well connected through a single wave vector, meaning that this term is going to diverge. This is called Fermi surface nesting, and in one dimension is very easy to get. When you have 2 dimensions, it's not easy to connect all your states of the same energy with the same wave vector. Therefore, this susceptibility does not diverge anymore. So this is the case just as of a metal in 2 dimensions. But if you have some other type of Fermi surface, which is not a regular metal in 2 dimensions, you can have sections or can have Fermi surfaces with sections that are very well nested with a single wave vector, which are susceptible to the formation of this charge density wave. So in 2 dimensions, we do have charge density waves. So this partial nesting creates more complicated effects. So I was telling you the charge density waves tend to make the material insulating in 1 dimension. But in 2 dimensions, when you have partial nesting of your Fermi surface, you can still have metallic states that are not nested by your Fermi surface. Therefore, you can have a combination of metallic states and portions of your Fermi surface that are gapped. So this is an example in niobium triselenide, in which you have 2 different transitions to a charge density wave due to 2 different wave vectors that nest different portions of the Fermi surface. And this, right at this transition, the resistance of the material increases because it opens a gap right at those transitions. But nevertheless, eventually the metallic state will win the fight, and then you have another transition to a charge density wave. So these charge density waves have many details that could complicate this landscape that we are trying to understand. So in addition to that, so a charge density wave, you can characterize it by a periodic arrangement of your charge density with a characteristic wave vector that is the one that nests your Fermi surface. So this picture that I'm telling you here is a picture that comes from Peierls, which considers only like the electronic point of view of this. This modulation also comes with an anomalous phonon structure in which you will have a Kohn anomaly, which is the softening of a phonon in the material, which also modulates the periodicity of your lattice in your system. But I'm giving you the flavor of the electronic side of it because I want to aim for some interesting topological states in the electronic structure and how that correlates with the charge density. So you have your charge density wave that opens a gap, and for this charge density wave, which in principle is a rigid charge density wave, you can take pictures of it with an STM, which looks very nice. But you can actually displace this charge density wave rigidly. So if you put an electric voltage in your material, and if your charge density wave is not pinned by impurities or other effects, you can actually transport rigidly this charge density wave. And the lowest energy excitation for this charge density wave is called a phason. Yes?
No, just question. Sorry.
So this phason will look something like this. You take this charge density wave modulation and you display the phase of it as a function of time, of course. And this creates a current. This creates a current, which will be the derivative of this phase of this charge density wave. And therefore, you will have, as you are increasing the current in your system, you can have metallic states, like for example here, you create an IV curve. You will have some metallic state that will give you some resistance of the material or some conductance. But once you hit the threshold voltage for which you can actually depend the charge density wave and transport it, you will increase the conductance of your system or decrease the resistivity. And you enter this highly non-linear regime of transport for this charge density wave. So this is a characteristic IV curve for this kind of system. So people like to look at it in terms of the differential conductance, because you have some normal metallically resistive system here for low currents, but if you hit the threshold current, you will have a lowering of this or an increase in the conductance, which is this signature that you have here, or lowering of your resistance. All right. Now, what happens if I mix topological states into this? Turns out that some time ago, Xusheng Shang and collaborators worked through this problem and realized that actually you have a material that has some pair of vial cones. And if you create a periodic modulation of charge in this kind of system, you can actually gap the vial points. And this gap will create a charge density wave in which the phase of this charge density wave will pick up the topological properties of the original band structure. So if you calculate the action of these guys, I don't follow all the details of this calculation, but you can actually arrive to a term in which the current that you have, if you put an electric field in this kind of system, this current will pick up a chiral anomaly. So if you put an electric field into this vial system, you will have this chiral anomaly, which will carry current with different chirality between the two different vial points. So this term will get picked up into the current of your charge density wave, meaning that your charge density wave will respond to magnetic fields. It will be natural for it to respond to magnetic field. But not only the charge density wave, it will be a sliding charge density wave in which you can actually have signatures of this chiral anomaly for this charge density wave system. All right. So has this been realized? It turns out that there is a couple of experimental observational experimental claims in this system, which is very close to the one I will show you today, which is the tantalum selenium 4-2 iodine. So this is a work by the group of Claudia Felser, and this material is also quasi-one-dimensional material in which some ARPES measurement plus DFT calculation have shown a series of vial points all across the first ribosome in the system. And Claudia Felser group measure conductance or IV curves that are characteristic of this chiral anomaly, meaning that when the magnetic field and the current or electric field in your system are parallel, you will have a maximum effect in the conductance in this system. So for different magnetic fields, you will have different effects for this compound. And as a function of angle, you can actually reproduce this E.B kind of term for the chiral anomaly. However, more recent studies have challenged this set of observations. So this is a recent measurement performed by, I don't remember the name of the group, but it's here in this it's a French group, and it's here in this publication, in which they have tried to reproduce this set of measurements, and they have been unable to reproduce this chiral anomaly kind of behavior. All right, so this is one example.
Could you go back? I don't see anything. Why is
Okay.
this not different from this one?
Because here, oh, sorry, I forgot to mention, these are two curves at different magnetic fields in which you are supposed to have a larger chiral. If your field increases, the effect of this chiral anomaly will increase, and they don't see any sort of effect. So this is for currents that are parallel to the magnetic field. They don't see any kind of difference. So they are unable to reproduce these kind of measurements here.
And what is your take? Also,
And just a question, why are measurements like 90, 80? Is there like phase transition call it, or why not lower?
Yeah, that's a good question. I have no idea why they haven't been lower. I'm not aware of a different transition that happens at lower temperatures, but I guess because they run out of budget to buy helium. That would be my case. But yeah, these are done at 90 and 80 Kelvin. Okay. So
So they're the same compound, yeah?
yes, it's
Are they
exactly the same compound.
Is it the same team that produced the compound, or different teams that produced it?
I think the methods are similar. So that in this group tested different different types of crystals, and they were unable to reproduce in any of the crystals they had this kind of data. So I'm not aware of any other group that have tried to reproduce. So right now it's an open question whether there are more subtleties to these type of measurements or not. So there is a very tricky experimental challenge with IV measurements. And is that if you put, because for these measurements you need to put large currents, right? This is an effect that happens above a threshold current. So if you put too much current through a material, you can heat it up. You can create some Joule heating, and this heating will actually increase or change your resistance. So if you're not very careful and if you don't thermally sink your samples very well, you can create these artificial effects in your IV curves. So this group here, which is a French group, I'm sorry, I forgot the name of the PI, but this group has been measuring IV curves in different charge density wave systems for many, many years. So it's not like someone just measured something and was unable to reproduce it. It's someone that knows what they're doing.
Yeah, no, I just curious on the graph, sorry, because it's this on the right graph, it's up to, you don't see the change up until 20 volts. The left
Yeah,
graph,
so this is a differential conductance. So
yeah, that's a differential conductance.
Mhm.
Yeah? And so on the left graph, you see it up to 4 volts, and on the right graph, you see it up to, different changes start happening to 20 volts. Right, more to the right, that's
right.
the differential conductance.
yeah, I mean,
That's
so
just,
there is another thing is that volt is not an intrinsic measure of things. It would be electric field. I'm not sure. So the voltage depends actually on the size. It's
yeah,
not
the sample and
when
things,
it's
yeah.
intrinsic. It depends on the sample. So they did what it's important here is that they hit the point in which they can displace the charge density wave, which is the important thing. If you have a chiral anomaly and you displace the charge density wave, in this type of system, if you play in this type of physics, it should have a chiral anomaly. The fashion of this charge.
But my question is, in the right graph,
Uh-huh.
it doesn't start. You don't start seeing the right farthest right on the bottom for the different
This?
conductance. The one on the differential conductance is a bit easier.
On the right.
To the right,
Here?
right.
The other right.
Yeah. So this doesn't what causes that spreading out. It doesn't happen. It doesn't feel
So
like it happens
this is
immediately.
precisely that as you increase magnetic field because you are parallel, you have
But
the
then
electric
after
field.
you engage I mean, maybe I'm blind. I can't see so far. But the spreading out of the as a function of the magnetic field doesn't feel like it happens directly after you start to transition.
So do you need to displace the charge density wave? So meaning
So
you
the
need to,
displacement happens around like 0.5 volts. Yeah, that BM there, is that correct?
no, yeah, but my point is that, yes, these are higher voltages, these are lower voltages. But the voltage is not important. It depends on the size of the sample.
That I agree.
What is important is that you have a nonlinear regime for the displacement of your charge density wave,
Yeah, so
meaning that you have this lowering.
what causes it to spread out though? And when does that
The-
start?
the-
When
the
is that
chiral-
when is that oncoming? It doesn't seem like it's with the start of the charge density. What causes it to spread out and when?
So the precisely the chiral anomaly. So meaning you will have a contribution of your conductance and your current through an E.B term. So this E.B term, if you increase the magnetic field, this E.B term will be stronger. So you would expect that you have a larger contribution for the nonlinear conductance for this regime here. And because it is in the regime in which your conductance is nonlinear, that you could claim that this is due to a displaced charge density wave, meaning a phason that picks up this chiral anomaly term.
So just to make sure, so if we compare B with F, the one directly above it,
B with F, yes.
so there the magnetic field is perpendicular to the electric field,
Exactly.
parallel to the electric field.
Exactly. So this is precisely their claim. When your field is perpendicular, you don't have the chiral anomaly. But when it's parallel, you have a maximum chiral anomaly. So meaning that you only have a contribution in the nonlinear regime of the phason displacement only in this situation and not in this one. So that's the whole point of that claim. Great. All right. So now I am not going to talk about that system. I am going to talk about a different one, which is also an interesting one. So the space group of these two types of materials is not the same. So that other system is supposed to be in a space group which allows the presence of biopoints. This one not necessarily. What has been predicted is that it has Dirac points. But nevertheless, it's interesting to explore if in those other systems in which there are biopoints and charge density waves, some interesting physics can come out of it. Why not in this type of system in which you have Dirac cones plus charge density wave? So let's explore this a little further. So this material has the similar kind of structure without the iodines that goes in the gaps as in the other material. And it's a quasi-1D compound in which you have these chains of tantalum or niobium atoms surrounded by two squares of tellurium that are rotated with respect to each other. So this compound has a tetragonal crystal structure, and the bonds along the chains are strong, and the bonds along the in-between chains are weak van der Waals interactions. So because it is a quasi-1D system, it's susceptible to the formation of a charge density wave, and indeed it forms a charge density wave below about 470 something Kelvin. So from very high up temperature. So these are some nice STM measurements that we took in niobium tellurium 4, in which you can actually see the periodic modulation in real space for this charge density wave. So you see these little cashews that have, in Spanish, we started with the name bananas, but maybe that was not very appropriate in English, so we call it cashews. So we have these cashews, and these cashews are actually groups of 3 different tellurium atoms. So if you cleave a surface, this is a natural cleavage plane. So you will see that the telluriums that are on top on the cleaved surface are actually these telluriums that form these kind of zigzag chains. So that's exactly what you see here. You see zigzag chains that groups 3 tellurium atoms, which form a trimer. So you see these zigzags, and this is actually the modulation of the charge density wave. So you see that it creates a superstructure. This modulation creates a superstructure that doubles the unit cell along the A direction and triples it along the Z direction, meaning the chain direction. And this periodicity is important because it will be related to the wave vector of the charge density wave. So we created like a model, a toy model, I cannot explain difficult things. I can only go to simple things like balls and sticks. So I have these balls, which are my atoms, and actually you can recreate this kind of superstructure by putting together two niobium or tantalum atoms. So you have a tantalum atom in the center and two tantalum atoms that come closer to this one, which actually deforms the positions of the telluriums that are on top and creates a large charge density right at that region and minimum charge density for these two niobium atoms that come apart. So this actually creates an asymmetric structure for the charge in each of these caches. And you can actually see that if you create like a more contrastful color plot for these caches. You see this asymmetry in the charge. So this means that the wave vector or the wavelength for this charge density wave is actually 3/2 of the C unit cell. All right, and if you check and you analyze adjacent chains, they actually have an AB stacking for these chains. And this whole configuration and superstructure can actually recreate most of the observation we have for the charge density wave. So something for you to realize is that this material was highly studied around the 60s, in which we didn't have very high resolution microscopy techniques. And this superstructure had not been directly observed before to this study. So this allowed us to actually recreate the full superstructure. So in addition to that, so those measurements were in niobium tellurium 4. But we have niobium tellurium 4 and tantalum tellurium 4. And although these two systems are very similar, they have differences. So this is the resistivity measurements for both of these systems. And this is a derivative of this resistivity, which highlight some of the features of the nature of transport in these two compounds. For instance, the tantalum tellurium 4, the resistance seems pretty flat. There are some features or some things that could be something. But for the niobium tellurium 4, there is a more obvious change in the derivative of this resistivity measurement. And around this 200 Kelvin temperature, many people in the electron microscopy community back then in the 60s reported a lot of peaks that arise that look like transition to incommensurate charge density waves. So we wanted to analyze if actually these type of things were real phase transitions to different charge density waves, thermodynamic phase transitions. And around 50 Kelvin, niobium tellurium 4 had been reported due to these electron microscopy studies to have a lock-in transition. Lock-in transition means a transition between an incommensurate charge density wave to a commensurate charge density wave. So we decided to actually study these kind of features. So the first thing we did was characterize actually the charge density wave right at this low temperature. So let me show you some extended version of these STM measurements. So for instance, we took larger areas images and we noticed that don't pay attention to this dirt that is here on the surface. What is important is actually the line, the things that go below that has some atomic periodicity. So if you check these lines here, these look like columnar defects or domain walls, which are actually that domain walls in this material. And we were able to recreate or to understand these domain walls through phase slips regions for the charge density wave. Meaning, if you see, for example, this domain, this is a zoom to some region that has some domain, you see that there is a change on the orientation of these peanuts that you have here, these cashews. And then if you model these with the simple models that I do, which are in Paint, so you have this kind of, you can explain that through these kind of things, to the merging of two of these peanuts. And actually, if you go to the atomic level, you can see that this is what recreates these kind of features. And if you come even closer, you can recreate what the charge density wave would be. So these two regions are separated or are originated through a change in the phase of the charge density wave on one side of this defect and the other side of this defect. And like that, you can have many types of defect that can be recreated by these facelift domains. So all the facelift will have jumps in 2π3 of the phase of the charge density wave, which is related to actually the periodicity of this charge density wave, because this displacement or this facelift comes from NC halves of the of motions between C halves is the distance between two different niobium atoms, so you can only have integer numbers of these displacement for the phase. All right. So this is what is called a discommensurate charge density wave, meaning you have a charge density wave that is not commensurate macroscopically, but if you go in little regions of the order of 10 nanometers, it's commensurate locally. So the origin of these
Quick
domain
question.
walls,
So you see this in the niobium compound, but not the tantalum compound?
exactly. So this only happens in the niobium, and that explains, for instance, things like this. Whoop. Like this. So why here you have different changes? So for the tantalum, you have nothing. For the niobium, you have these sort of changes. So we wanted to know if these were transitions to different characteristics of that charge density wave. But what we realized, and in order to see and to characterize that as a transition or not, real thermodynamic transition, was what we did is, which I'm going to show you later.
Just to make sure I understand, so you're not saying that you have an incommensurate charge density wave, you're just saying that you have domains.
Yes, the charge density wave is commensurate, but they can change. These commensurate regions can change phase in some domains or at some regions, which makes it a discommensurate charge density wave. But locally, like if you calculate things, what comes out of that calculation, if you had a perfect system, is always a commensurate charge density wave. The discommensuration is just a subtlety that arises in that particular system.
Does the niobium system have more defects in it?
So that's exactly my previous slide that I was going to skip because I won't have time. But what we did is we tried to figure out what kind of defects are these. Is there vacancies that you can have, columnar vacancies in your system, or some kind of additional atoms that sit on top of the surface? So we did high resolution transmission electron microscopy measurements, and these changes of colors are due to different contrast or different thickness in your sample, but all across you can see lines of atoms. It's not that you see a line with voids all across your system that could explain these defects or these domain walls. So we don't think these domain walls are physical, are voids. These are electronical. These defects have electronic origin. These are jumps in the charge density wave that for some reason happen in that system.
And the assumption is that they appear macroscopic. It's not just an absolute finite density.
Exactly. They have finite density and they are actually dynamical. So our claim is that all these transitions and changes that you see in the resistivity are not a consequence of a real phase transition. These are actually highly hysteretical. So these domain walls can easily move across, which an electronic defect will have more flexibility or lower energy barrier to actually move across than a real vacancy in the system. So they are highly movable. And we tested this through this nice technique that we have in our lab, which is called resonant ultrasound spectroscopy, in which you can actually measure some quantity or resonances that are proportional to the elastic constant in your system. So the elastic tensor in the system, I will show you in a minute. Let me first explain to you this technique, how it works. So you have a sample that you put in between two different transducers, and you create a perturbation, a harmonic perturbation in one of the transducer and measure in the other one. So this is how the real thing looks, and these are our beautiful millimeter size samples. So this can be challenging to measure this thing. But this is basically what we are doing is a resonance experiment. So if you have a forced harmonic oscillator and you resonate, you know that if you create this periodic perturbation, you have one resonance for the system, and that frequency of resonance is directly related to the constant of the spring. So we are basically doing that in a three-dimensional version here. So what we do is that we create this harmonic perturbation and we measure the resonance positions in frequency for the sample. And this spectrum of resonances is directly related to the spring constant, which actually is the second derivative of the potential of your system with respect to deformation, which is actually in 3 dimensions is the elastic tensor. So each of these resonances is related to a component in symmetry of the elastic tensor. Yes.
So the way you show the crystal orientation, it's not along a high symmetry direction, is that so you pick up all the different modes?
Yes.
Okay.
So you want to have as close as possible to free boundary conditions. So you can actually, because the idea is that you don't want to measure just the frequencies. You want to go directly to the elastic constant. In order to do that, you need a numerical problem. Because if you know the elastic constant, you solve your Lagrangian and then you get the resonance frequency. But going backwards needs to be done computationally. So in order to do that, you need to have a perfect boundary conditions, which in this case are free boundary conditions. So that's why we picked it from the corners. Yes. Yes. All right. So you can actually have information of these elastic constants, which are quantities that are a derivative of the free energy of your system. Therefore, it's a thermodynamic quantity. If you have a thermodynamic phase transition, you would expect to see jumps in this quantity. So the frequencies are actually proportional to these elastic constants. So there are more complications into these details that I'm going to skip for the matter of time. But if you believe me, you can actually take each of these frequencies and track what they are doing in temperature, how they move in temperature. And through this motion, you can actually relate how these elastic constants are changing with temperature, and especially across a phase transition. So you take each of these frequencies, this is one that we're tracking, and you can actually track how it moves with temperature and how the width of this resonance is moving as well, because that will give you an idea of dissipation, which you will expect to increase when you cross a phase transition. And you can actually do that for all the different resonance in your system. So this is how the frequencies are changing as a function of temperature and the width of these resonances. So for tantalum tellurium-4, we see there are some jumps that are some technical details with the thermal stability of the things that you don't need to pay attention to. What you need to pay attention to is the gross differences between the tantalum tellurium-4 and the niobium tellurium-4 for process of cooling and heating, which means thermal hysteresis effect for the niobium tellurium-4 and not for the tantalum tellurium-4. So this thermal hysteresis effect means that you actually have highly movable domain walls in the system that comes all across for all the different ranges of temperature. And this resembles results that have been taken for similar system, but for granular system in engineering, in which you have these grains with these movable frontiers that actually have the same hysteretic effects. So the message of this, and why am I boring you with all these kind of details, and is because if you want to say that something is topological, you can come across with these kind of things. This is complicated, and this can mask the interesting physics that you have behind. So you need to understand this detail before you come into saying that something has more exotic physics. So we have done our work.
So what about like photo emission? Is it not possible here for some reason?
Yes, I'll show you for emission in a second. So another thing I want to tell you is that niobium tellurium-4 with these highly movable electronic domains creates a lot of scattering. So these are magnetoresistance measurements for tantalum tellurium-4 and for niobium tellurium-4. And you see that the magnetoresistance is highly suppressed for the niobium tellurium-4. Meaning these two systems may have a very similar electronic structure, just that these electronic effects are masked by these highly movable domain walls in the niobium tellurium-4. So therefore, in order to reveal the full glory of this electronic structure, we focus on the tantalum tellurium form. So I'm going to show you how we did this, and I'm going to show you some RPS measurement for that compound. Okay, so tantalum tellurium 4 and niobium tellurium 4 have very similar electronic structure as calculated from DFT with my collaborators. So they have a pair of Dirac points across the gamma M and gamma Z direction of the Brillouin zone for both of them. But they have very different transport properties. So just to highlight that fact that these obscure details or these complicated details can create strong differences for the scattering of these two systems.
Is there a gap in these cones, or is this?
No, there is no gap. They have measured that it's a real crossing.
And the other ones, the other crossings on the left or left, no, below.
I think the only one that have a Dirac or
the other ones no.
topological characters are these ones here. They have checked. Right. So how can we reveal the electronic structure? So one method is RPS, which will give you access to surface states, but we wanted to go into a more thermodynamic way of determining the bulk crystal structure for this compound. And the best technique to do that is to measure quantum oscillation or Shubnikov-de-Haas effect, which is tracking the oscillation that you have as you quantize electronic orbits in a magnetic field for the system. So let's start with something basic. You have if you have a metal, you have a Fermi energy. So you have a Fermi surface, which is a circle. Then once you have a periodic arrangement, you open gaps and your crystals, your bands become really complicated. You don't have circles anymore. So this is an example for gallium FCC structure. So you have a Fermi energy here, which creates a set of pockets right at the gamma point and right here at the L point. And you can visualize these in this FCC Brillouin zone as pockets that go in these L points and the gamma points here. So you don't have a sphere anymore. You have these different pockets that are oriented differently in different regions of space. So the structure of gallium arsenide is very similar to the one of lead telluride, which is the interesting compound that Greg was mentioning earlier. So for lead telluride, for example, you have these pockets here at the L point and some predicted pockets here that form this cage kind of structure, which turns out that they don't get to that point ever. So the Fermi surface is actually very simple. It's just these ellipsoids that go, these ellipsoids that are in these L points. So in order to characterize and really know if the electronic structure is that, so we use what's called quantum oscillations, which comes from the quantization of the electronic orbits in a magnetic field. So you have a metallic Fermi surface, a sphere. You quantize the density of states into the Landau tubes, and the spacing between these Landau tubes is actually proportional to the magnetic field. So when you start sweeping magnetic field, these tubes start to cross out the Fermi surface, and each of these cross out generates anomaly in the density of states, and therefore all the quantities that depend on it, for example, the resistivity. This crossing of these tubes is periodic not with field, but with the inverse of magnetic field. So you have things that will have a frequency that will be of the units of Tesla, because it's in the periodicity is the inverse field. All right. So, and this comes from the flux quantization for each of these Landau tubes as well. So you can write this on-Sager relation in terms of the quantum flux and then the area of your Fermi surface here. All right. So each of these crossing out of these Landau tubes generates these jumps in a quantity that is directly proportional to the density of states, like for example the resistivity. And if you put the magnetic field across different directions, you will have an evolution of the frequency components of these oscillations. So you have other terms that gives you different amplitudes from which you can actually obtain things like the effective mass of carriers. You can obtain the relaxation time for your carriers, and you can even deduce G factors for this kind of system. So these are quantities that you plug in your computers that we can actually measure directly from this type of experiments. So the amount of information from quantum oscillation is very complete. And I will show you in a minute what we can get. So you can get
these results are by band, yeah? Or do you have
By band, yes, exactly. So I'll show you a more complicated, because I show you the example of the spherical one. This is not a spherical Fermi surface, and I'll show you why. So you can actually, if you rotate your magnetic field along different directions, you can actually cross different cross-sectional areas of this Fermi surface. And by tracking how this evolves as you orient your magnetic field along different directions, you can actually deduce what's the shape of your Fermi surface. So this is what we have done, for example, for the system. This was a predicted Fermi surface, and this is the evolution. These two pockets, if you orient the field along some plane, and you start from 0 here and then rotate, you will expect that these pockets will give you an evolution of the cross-sectional area that go like this, meaning that around 40-something, 50-something degrees, 54 degrees, you will have the minimum cross-sectional area for these pockets. But you can also have, for the same angle, an evolution or a different frequency component for other cuts of other pockets that you have here. So this will be the evolution of the cross-sectional area for these two pockets here. And even for these other ones, which form a plane perpendicular to the plane in which you are rotating magnetic field. So these plots can get really, really complicated. A sphere would be something flat, right? It's the same cross-sectional area across all the different directions that you measure. And even you can resolve things like if you are misaligned in your plane of rotation, you can have splittings in these paths of the cross-sectional areas. And you have other harmonics of the signal. So now you can anticipate that this can get really complicated because you have for one angle, you have all these frequency components for a Fermi surface, which is not that complicated, like in the late Telluride. So you take your data, you take the non-oscillatory component, you plot it as a function for different angles, you plot it as a function of inverse field, and you take a Fourier transform in order to get the frequency component of this. So this is your Fourier transform. You can plot it in a nicer way to compare it directly to what the plots I was showing you before, to compare directly with the theory, and then you get these nice plots. And then from these nice plots, you can actually compare with the expected evolution for the predicted Fermi surface. And you can get exactly the sizes of your pockets, the anisotropy, effective masses, whatnot. So this is exactly the procedure that we have done for the tantalum tellurium 4 in order to resolve the Fermi surface. You have this, which looks very complicated. This has a lot of frequency components, And the Fermi surface is not as simple as the lead telluride that I was showing you before. So this is assembling a puzzle, completely assembling a puzzle, which I try to do my best. So in order to have all the pieces for this puzzle, you need to rotate. If you only rotate a magnetic field across one plane, you will have limited information. You will need another plane in order to reconstruct, or another set of planes in order to reconstruct all the different cross-sectional area and map out the three-dimensional Fermi surface. So what we have done is that we took data rotating, putting current along the chain direction, which we call C, and rotate the magnetic field in a plane perpendicular to that current direction, and that magnifies the magnetoresistance for all the different directions. But we also rotate it in a plane that goes from A to Z, in which you can actually, going from A to C, you go in a direction in which magnetic field is parallel to the current. That suppresses completely the magnetoresistance. This has some level, artificial level, but this is 0. The magnetoresistance for that is 0 when your magnetic field is parallel. But also the oscillatory component is 0, which is something I still don't understand why. So I invite you guys to explain to me how that can happen. Okay. And because of that suppression, we decided to go into a very complicated endeavor. Yes.
Great question. Are your samples thin, so you might get a contribution from like two-dimensional surface states or something like that?
The samples are not that thin. They are long needles, and they have some square cross sections, but they are long, of the order of a ratio 4 to 1 in this direction, but 1 to 1 in the plane. So they are of the order of 1 millimeter long, 0.4, 0.5, or 0.4, 0.2 millimeter on the side, but they are square. They are not micron thin or anything like it.
So you think your only contributions are bulk contributions?
I do think so. Yeah, they are not that thin. I mean, they are of the order of millimeters anyway. So, but these samples have a very, very strong challenge. They grow very long, and cutting them in the perpendicular direction to the chains is really, really difficult. So we went in an endeavor of trying to grow samples that are actually fatter than the ones we were growing. So we were using a growth technique that is called flux method that grows very nice long needles, but we needed to modify our method in order to grow fatter crystals, in which we can actually put the current along the A direction so that we can sweep from A to C being perpendicular to the current in order to not suppress this magnetoresistance for these samples. So this took us years to actually refine these kind of methods to put the current along A. And the results I'm going to show you are full new, and we are preparing the publication for this. So these are kind of the samples you have. This is a fatter sample, but it's this long. You need to put 4 wires in these samples. So if you think of putting the 4 wires in the perpendicular direction, that's a nightmare. And if you think of doing interesting things like the ones you care about, like Hall, that's a complete nightmare to do Hall in these kind of samples. So, but we are working on it. So in this plane that you do have still some suppression of the magnetoresistance, but you can observe really nice quantum oscillations. So how much time do I have? 4 minutes? Okay, so I'll run. All right. All right. So we take our magnetoresistance, beautiful, as a function of inverse field. We plot our Fourier transform as a contour plot, so you can see all the frequency components. And then now what? I didn't have the information of a nice simple Fermi surface. What can I do with this?
We ask Emil.
You ask me, yes.
I should have in Charlie.
And then not only that, this is in the regime of 1,000 Tesla. But if you go to a low frequency regime, 200 Tesla, you also see a bunch of frequency components. So this is way more complicated than you would wish. So then we rely on what we know. So we go to ARPES to have some lights into this, and to our DFT friends. So ARPES, for the first time, so these are very recent papers, 3 different papers from last year that measure ARPES and observe for the first time metallic state in the system. And this was a big question for many, many years because previous ARPES measurement never observed states at the Fermi energy. So we needed an improvement in resolution for this ARPES technique in order to observe very weak metallic states. And this material is a very good metal, actually. Micro centimeter kind of resistivity for this system. So they have metallic state. All 3 studies in which we participate in this one with our samples, they all show metallic state at the Fermi level. So now we can actually recreate a Fermi surface for this compound. So it turns out that all 3 studies showed Fermi surface that follow the periodicity of the undistorted compound, meaning not the periodicity of the charge density wave, which is what you would expect if you had a reconstructed, of course, Fermi surface from this new periodicity. But we see things that have the periodicity of the original undistorted cell, and this is the Brillouin. In addition, they observe some strange states here that if you zoom in and they get interpreted, this is very nice because they are complementary works. They interpret in a different kind of perspective this material and this result. So for example, this work from Mingyi and Rice, they actually see the bands that have the periodicity of the undistorted cell, but they also see some bands that do have the periodicity of the charge density wave. So which are these ones here, they are very weak, and they actually create very small pockets like these ones here in this cell. So good, we have large pockets like these ones, and we have small pockets. So we have large frequencies and we have small frequencies. So that's the first thing that we needed. This other work also identify this kind of a spectral wave here in the regions where the Mingy sees these small pockets. And they also they see the periodicity of the charge density wave for these compounds. And they calculated band structure for the system, and they realized that that these two bands that crosses here that form these Dirac points actually have different orbital character, and these bands get reconstructed differently depending on the orbital character. Meaning the orbits that have a large C component, get reconstructed more aggressively than the ones that have an in-plane component. So this, they call it orbital selective charge density wave reconstructions for this material. So it's quite complicated. So for the analysis we performed, we realized that actually these points in which you see these additional spectral waves, which are the ones in which the charge density wave is reconstructed, are actually right at the positions in which the Dirac points project into that surface. So they are the positions of the Dirac points, which actually makes me think that spectral wave is actually a reconstructed Fermi pocket, or is some surface states that you see there right at those positions? What are those? So these are nice open questions for this compound. All right. So what we did is, with all that and with our DFT friends, we tried to search for things. So large pockets. The ARPES pockets of the non-CDW reconstructed things are of the order, if you use the on-site relation, they should be of the order of 4,000 to 5,000 Tesla, the cross-sectional area. We see nothing at that. So we don't see the large pockets that they observe in ARPES, which is a mystery.
Wait, are those units right? I mean, you can actually, where you get a 4,000 Tesla?
So that's the nice thing about this kind of experiments. We measure only to 35 Tesla. The largest magnetic field that you can actually go and use is 300 Tesla, and you blow up your experiment in pulse fields. We can only access 35, but I'm not talking about the real magnetic field that you are putting. This is a frequency unit. So because of this on-site relation, the cross-sectional areas, because this motion of the lambda levels is periodic in the inverse field, so the frequency has the units of Tesla. So it just characterizes the sizes of the Fermi surface.
That's not the physical field.
It's not a physical field, no.
Okay.
It's not a physical field. So that's
Okay.
some important to remember. So we don't see any frequency components of 4,000. Yeah, I'm going to show you that we do have it, because we do observe in the other nice plane with the nice phasey crystals that we grew, we do observe some features at that frequency.
So one question is that kind of focused my attention. So you presented all this beautiful data on the Fermi surface measurement, and then the photo emission. What is the target that you're going for? Are you trying to see if there are wild points?
Yes,
there?
I'm trying to see if there are signatures of Dirac points, which
Dirac
we think
or
we
wild?
observe.
Are you distinguishing the two, or?
The calculations show that they are Dirac points.
Okay.
Yes, not wild. Mm-hmm.
Is that different from the Novium report, which was shown before, the previous results from the two groups? So
Which ones?
The two groups that you compared earlier, the charge density wave.
I mean, for the ARPES measurement, you mean?
No, you showed the charge density wave of two groups experimentally. Those are wild points or also direct points?
They are Dirac points.
Oh.
For all of the studies and all the calculations, they predict that they are Dirac points. Mm-hmm.
And is that because you don't have broken inversion symmetry? I guess there's no broken time reversal because it's not magnetic.
I mean, the group, because in tantalum, selenium for iodine, it is a different space group that this calculation have shown that specific space group has or allows the symmetry for the presence of bio points. For this one, I am not sure, and I invite you to help me to find these answers symmetry-wise. But the calculations that they have done, they tell me that these are direct. And all the different, there are 3 different publications that show that they are direct. But symmetry-wise, I'm not sure.
Okay, and those are first principles calculations you're referring to?
Yes.
Okay, yeah, it must just be that it has inversion symmetry.
Okay.
And then there's no magnetic order here.
Yeah, there is
I
no
think that's
magnetic.
probably just.
All right. So here we see, so if we focus now in the lower, so for the higher frequencies, we have nothing. For the lower frequencies, which are of the order of frequencies predicted by this reconstructed Fermi surface from ARPES, if you calculate this cross-sectional areas, the frequency range would be of the order of 200 Tesla, and we do see a lot around 200 Tesla. So we first of all recognize this path of evolution, and this comes from the same set of pockets. So I told you that if you have one set of pockets, you can have many different paths for this evolution. So the predicted Fermi surface from our DFT calculations predict this nice set of pockets that are consistent, which evolution in this plane of rotation is consistent with this evolution that we see here. Size-wise, it's not that easy. So you can have a mismatch in the Fermi level in the system in DFT. From what I understand, it's very easy to have a mismatch in the Fermi level. So we are not comparing in terms of sizes, but in terms of geometry or shapes of these pockets. So this is what we have here. Now we see a second set of evolution, which is much weaker, but has exactly the same kind of evolution that these original purple ones. And this is also predicted in the reconstructed Fermi surface that we have from DFT. Now, you observe a bunch of harmonics, which is actually something very, very impressive. We see up to the 5th harmonic for these frequencies, which implies that literally the electrons are going 5 turns around these Landau levels before they scatter and they get lost. So the coherence or the purity of the samples need to be very good in order for you to observe these higher harmonics. And you need to go to high fields in order to have these resolutions.
What temperature does the experiment?
This is 1.3 Kelvin. Yes.
There are some relationship with these harmonic and Fourier phase, for example.
So we know we can have, so I'm going to skip really fast to that point now because time. Thank you. But I'm going to show you how you can deduce very phase, and you can refine it, and we are in that process to refine that very phase calculation, but the like measurement, you would say, with the higher harmonics. But we are in that process. So you see many, many features that implies a very complicated Fermi surface. So for instance, there is this Fermi surface which actually creates closed orbits in some direction, but open orbits in different directions. So it's really, really assembling a puzzle to actually deduce this Fermi surface for this compound. But I think we have been pretty successful at determining what actually the Fermi surface looks like, because we can map all the different frequencies that we observe, we can map it into the DFT calculation. So that worked very well. So this is the additional plane. So one very important feature that we see in this additional plane is that we see first of all, we see the 4,000 frequency that we were missing. That it's of the order of magnitude of the sizes of pockets that we are seeing in ARPES, meaning that in transport we also can see sections of Fermi surface that are reconstructed and sections that are not. All right, and oops, I don't know why it looks like that. And also we see some sections that are very two-dimensional sections, like cylinders that we see in this compound that had not been identified before by any type of study. So this is the Fermi surface that we look. If you take a look at the positions of the Dirac points in this compound in momentum space, you would expect to observe that this set of pockets encloses a Dirac point, and this other set of pockets enclose Weyl points. So what we did was we performed, this is the last thing I will say, we did fan diagrams, which is the way of extracting the Berry phase for this pocket. So meaning the quantization of the magnetic flux in this system into this phase, it will be 2 pi and the Landau index, then the 1/2, and the Berry phase will be there because we are doing closed orbits in momentum space, and this delta, which is a geometric factor that comes from warping or from three-dimensional versions of Fermi surfaces. So it can either be, it can be distributed between -1/8 and 1/8. So if you plot the Landau index as a function of inverse field, you will see that this quantity is the intercept. And from the intercept of this curve, you can actually deduce what the Berry phase is. So we have done that. But because our samples have many frequencies in their magnetic resistance, we need to filter all the other frequencies, focus on the one we are interested at, index the Landau levels, and then plot these kind of plots. So these are actually, you're using the magnetic fields from which these Landau tubes are actually crossing out the Fermi surface, which I find very beautiful. And you can actually deduce when the first Landau level crosses, the second, the third, these are very low frequencies, so that's why the Landau indices are very low. And if you subtract the intercept, you can actually deduce if the Berry phase would be trivial or it would be non-trivial. So what we did exactly that. Most of the people do for one set of measurement from one angle. We have performed for all the different angles the same kind of analysis, and we have found that this region would be a trivial Berry phase or a Berry phase equal to 0, and these would be regions in which the Berry phase would be expected to be non-trivial. So what we see for these pockets is that for most of the angles that we have, except some outliers, we have a non-trivial value for the Berry phase. And this for this pocket in which we would expect the Dirac point to be enclosed, and for these other ones in which also it would be enclosed. So that's how we get information about these complicated intricacies of Fermi surfaces of material. Thank you very much for your attention.